Top-performing AI forecasting systems are now reaching the accuracy levels of skilled human forecasters. They achieve this by taking off-the-shelf large language models and wrapping them in specialized scaffolding designed for context gathering and reasoning. These systems generally follow a multi-stage process. A question enters the pipeline, evidence is gathered, and the LLM outputs a probability. But due to costs and latency, systems operate under a fixed budget of LLM calls, defined as B. In production, B is exactly 5 inferences. This constraint creates a specific optimization problem. With exactly 5 calls to make, the system must decide how to distribute those requests across available models to produce the most accurate final prediction. This allocation strategy is a key architectural decision that must be finalized before a compound model is moved into production. The standard industry approach is to rely on leaderboard rankings. The simplest heuristic is to identify the single highest scoring model and allocate the entire 5-call budget to that one engine. A slightly more varied approach involves splitting the budget uniformly among the top 3 highest scoring frontier models on the market. However, data from the Metaculus Q2 2025 AI benchmark tournament suggests that these intuitive leaderboard-driven strategies may result in suboptimal performance for the ensemble as a whole. This indicates that achieving higher accuracy might depend on the relationship between models' predictive distributions, rather than just their individual rankings. Focusing on solo accuracy while ignoring how models correlate with each other appears to create a ceiling on the system's overall predictive potential. To investigate this, researchers analyzed a pool of 5 forecasters: 4 off-the-shelf frontier LLMs, Gemini 3 Pro, GPT-5, Grok 4, and Kimi K2.5, and 1 model fine-tuned on forecasting data, known as FT-GPT-OS-120B. This scatter plot maps each model's solo score against its divergence from Gemini 3 Pro. GPT-5 and Kimi K2.5 cluster in the high score zone, with very low divergence. This frontier cluster represents highly accurate but correlated models. Their reasoning and errors tend to overlap. This creates diminishing returns when sampling the same cluster. However, Grok 4 and the fine-tuned models sit much further to the right, maintaining high scores with significantly higher divergence. These structural outliers indicate complementary error profiles, offering information frontier models do not. Shared training data and alignment techniques in most frontier models create a performance limit when they are ensembled without more diverse alternatives. Moving beyond pairs, we can visualize how these models interact by looking at 3-way mixing weights on a unified landscape. This heat map displays scores across weight combinations. Moving along the bottom edge between the 2 frontier models shows a flat gradient with minimal gain, but shifting weight toward the fine-tuned model at the top vertex steeply increases the score. In this optimal allocation, the more diverse fine-tuned model accounts for 56%. In a real deployment, we must move from theoretical weights back to a discrete 5 inference budget. By testing all 101 valid integer allocations for a B equals 5 budget, researchers found the mathematically optimal team: 2 parts fine-tuned model, 1 part Gemini, 1 part GPT-5, and 1 part Grok. To find the most critical components of this team, we look at replaceability. This measures the exact score drop the ensemble suffers if a specific model is removed and the remaining models are re-optimized. This bar graph shows replaceability metrics for the optimal 5-part team. Removing Grok 4 causes the largest drop in accuracy, 1.7 points, making it the most critical member. Removing GPT-5 or Gemini 3 Pro costs less than 0.1 points. This reveals a counterintuitive result. Grok 4 ranks 3rd in individual accuracy, but it is the most irreplaceable member of the production ensemble. While GPT-5 and Gemini provide high individual skill, they are essentially interchangeable. Grok 4's value comes from the fact that its signal is not correlated with the others. These findings are grounded in classical ensemble theory, specifically the ambiguity decomposition theorem introduced in 1994. The first part of the equation shows that an ensemble's error starts as the simple average of its individual members' errors. The second part is the diversity term, representing how much individual predictions differ from the overall mean. Mathematically, an ensemble improves to the extent that its members disagree. This diversity subtracts from the total error. This decomposition has been proven to hold true for various scoring methods, including the log score used in high-level AI forecasting. The replaceability of Grok 4 is a direct reflection of this diversity term. Its value lies in its ability to maximize that subtraction. This means a model with lower individual accuracy can still reduce the entire system's error, provided it is sufficiently different from the other models in the pool. Optimizing these systems involves balancing individual member accuracy against structural diversity to minimize the total error. We can compare two different designs. Pipeline A uses all 5 of its calls on the single highest scoring LLM. Pipeline B uses a diverse allocation of different models. Even though both pipelines cost the same, Pipeline B is more likely to capture edge cases and avoid the shared errors that lead to redundant failures. For researchers, this suggests a new approach. A model should be judged by its marginal contribution to the ensemble, not just its solo benchmark score. System designers should look for models with distinct pre-training or specialized fine-tuning. These differences are what provide the necessary decorrelation. By treating models as specialized components with complementary error spaces, AI development moves from a simple compute scaling problem into a task of strategic composition. The core fallacy in model selection is the assumption that all AI errors are identically distributed. When top models share the same flaws, stacking them together does not solve the problem. The data shows that models ranking 3rd or 4th in individual capability can be the ones that determine the ultimate success of the system. In multi-agent pipelines, diversity is a mathematical requirement for reducing error. The purpose of a multi-model ensemble is to neutralize correlated errors through disagreement. The strength of a frontier AI architecture comes from its capacity for orchestrated dissent.